So we will get this going. Yeah, good morning. My name is Travis. I'm a technician here at Aprovecho Research Center in Oregon. And this is the latest in our spring webinar series. Today, we're going to be talking about emission testing. Going to have a little overview of both the test methodology as well as the equipment that we use to gather data and take measurements and come up with our test results. So we'll just kind of jump in here. Again, we'll be looking at the ISO 19867-1 cookstove test methodology. This is the standard that we use in the labs to compare different cookstoves. It's going to be measuring the emissions as well as the thermal efficiency. There's safety and durability aspects as well. We won't be covering those today. That'll come in a later webinar. We'll be looking at the equipment that is used both to perform the test as well as to gather and validate the data. We'll be having another look at both the quality control procedures that we use for validating the data at the end of the test, as well as doing the calculations to convert it into useful and meaningful numbers that we can use for comparisons. We'll also have a brief look at the data processing applications. We'll have a little question and answer session at the end as well. ISO 19867 is generally testing procedures for the lab. So it describes exactly how to do the test, each step in detail. It's going to cover equipment specifications as far as what exactly is needed. Talks about the data validation procedures and the conversions into the different test metrics, as well as the calculations used. Some of the equipment that we use in the lab is related for gathering this data, and some of it is for validating the data. The ISO water boiling test, or WBT, provides a method for comparisons of different cooking systems, but it does not necessarily represent the way the stove will actually get used in the field. This is important to note that when we perform the test in the lab, we do our best to operate the stove in a manner that is representative of how it will be used in the field. Both the fuel size, the pot that is used, and the operation itself. The test is optimized for continuous fed wood burning stoves, so rocket stoves, firewood stoves, but it does contain methods for batch fed stoves such as charcoal or pellet stoves like T-LUDs. The test protocol is flexible since it does prioritize instruction from the manufacturer to describe the cooking system and how it's used. Again, this is important as it covers different regional differences in cooking styles, common kitchen equipment, and fuel as well. It plays a very large role. The standard itself is voluntary. Many countries have adopted the tier system as far as how they choose which stoves can be used and can be sold within the country or within certain regions. So determining the cooking system, again, is a very, very important part of providing valid and meaningful data, using a pot that is similar to what cooks are actually using in the field, using fuel, again, be that pellets of a certain type or a certain style. Here in Oregon, we have Douglas fir all around us, so we tend to use Douglas fir pellets in the lab if we're testing a pellet stove. But in certain countries, there are many different recipes for pellet fuels, bamboo and sugarcane and many, many others that do perform differently in the stove. So testing the stove with local specific fuel, very, very important. The stove operator is also a very, very large factor in the whole cooking system as well. You can see on the bottom right is an image of one of the live outputs of one of our tests here in the lab, and some of the little bits of tape on the right side of the computer monitor there are in place so that when we are operating the rocket stove, we're aiming for a certain power level, and we're trying to maintain that throughout the phase. So being able to, again, simulate what the user would be doing, say, if they were trying to boil water at home. The standard test sequence of a water boiling test generally consists of 3 different phases: a high power, medium power, and low power. You know that for boiling water, we want the stove to be operating at high power, but for simmering and cooking rice or cooking beans, we want very, very low power. So a stove that is able to, if the stove does have different power levels, it's tested at the highest, the lowest, and a midpoint in between. The performance of the stove can vary greatly depending on the power level. Each test phase is generally about 30 minutes of actual burn time, including followed by a shutdown period or a cool down period of either 5 minutes or a 5-degree drop in the temperature of the water. Each phase should be started within about 5 minutes of each other. So we have a cold start, high power phase, followed by a hot start, medium power, and a hot start, low power phase. As far as defining each firepower level, high power, again, is going to be the maximum possible by the stove, which is normally defined by the manufacturer, or often by, if there's an air adjustment, it would be the largest possible amount of air going into the stove get you high power. But if field data is available that says that a stove is not used at its maximum possible power all the time, and there's a high power that is commonly used in the field, that should be the high power used in your test as well, if that's going to be the realistic use of the stove. The water does not necessarily need to boil during the 30-minute test period, although the stove does need to show that it can boil water at some time period at its high power, even if it doesn't do that during the 30-minute test period. Firepower must be high enough to bring the water to within 1 degree of boiling without a time limit, again. So if it does not reach this temperature after 30 minutes, a separate test can be performed to prove that it is possible to boil water. Medium power will be approximately halfway between high power and low firepower, and low will be the lowest possible firepower that the stove can produce. So again, if there is an air adjustment or a firepower level adjuster on the stove of some sort, the lowest possible would be used for low power here. The entire ISO test essentially boils down to this slide here, which are the tier ratings. So the full water boiling test is performed in the lab. We gather and then process a lot of different factors for the data that is collected. And the final calculations end up with results for the thermal efficiency of the stove and emissions of the stove. And in this case, the tier ratings are based on emissions for CO, carbon monoxide, and PM 2.5. The rating system is a 0 through 5, with 0 being the lowest performers and 5 being the best performing stoves. So a stove that has greater than 50% thermal efficiency, less than 3 grams per megajoule delivered of carbon monoxide, and less than 5 milligrams per megajoule delivered of PM 2.5 would achieve a tier 5, so a absolute top tier rating. The data collection and analysis that is required for the ISO test is broken down in this slide here into its most basic components. So we take measurements in the lab while we're doing the test. We're measuring the temperature of the water as well as the temperature of the air going through the collection tunnel. We measure the masses of the water and the fuel, as well as the mass of the PM 2.5 that gets collected on a filter. We'll be measuring the air pollutant concentrations of carbon monoxide, carbon dioxide, and PM 2.5. We measure the air velocity inside of our dilution tunnel, and a few other measurements are going to be collected as well. Once we have all our data collected, it gets processed. In our case, at Aprovecho, we have developed a application that streamlines the process, does all the calculations for you, and presents a nice form to analyze that data after the fact. The metrics that get calculated and eventually reported are going to be the cooking power of the stove in watts, the thermal efficiency. We will calculate both emission factors as well as emission rates, the fuel burning rate, as well as many, many other metrics. This all ends up giving us our tiers of performance, both again in thermal efficiency, in carbon monoxide emissions, and PM 2.5 emissions. The ISO protocol does also touch on safety and durability. And again, those will be described in a later webinar. Thermal efficiency measurements are actually one of the easier things to measure in a more simple lab. It does not necessarily require all of the equipment that we're going to be discussing in the rest of this session today. Thermal efficiency can basically be measured with just a thermocouple, a temperature for your water, and then gathering the mass of the fuel used as well as the water. Again, here in the lab, and a system that we've developed at Aprovecho, using the sensor boxes, something that we're able to do is digitally and automatically record all of our data. One of the main benefits of our LEM system. You can see the screen capture here is from our live data logging software. So this is an image from an actual test. You can see our blue line is the CO2, the pink line is the temperature of the water, the red line is the carbon monoxide, and the small black line at the bottom is our PM 2.5. So not only are we able to watch what is happening in real time, we're also logging and recording all of this data to be processed later. So you've heard me talk a little bit about the LEMs and our data collection and equipment setup. The LEMs in its brief form is a way to measure the cookstove emission rates following 19867-1. The system was developed by Aprovecho engineers back in 2005 and has been in use in several different forms since then. It is a total capture cookstove emission sampler, meaning that all the emissions exiting the stove are able to be captured inside of the hood and the dilution tunnel. We measure carbon dioxide, carbon monoxide, particulate matter, the water temperature, as well as several other metrics inside of our dilution tunnel at 0.5 hertz. So every 2 seconds, the sensors are taking recordings and sending them back and logging them to the computer. The PM 2.5 is also collected via pump and a filter setup. So we're able to collect a sample of particulate matter and weigh that by combining the temperature inside of the duct and the flow rate inside the duct as well. We're able to convert the gas emissions into a mass rate. The carbon dioxide and carbon monoxide sensors get calibrated against reference gases regularly to ensure that they are accurate. And the LEMS, again, it's an integrated platform for all the digital measurements needed for cookstove evaluations. LEMS consists mainly of a dilution tunnel, which is a series of pipes and ductwork that connects the hood, the collection hood, to the rest of the system. The long dilution tunnel helps to ensure that the sample is adequately mixed. It also helps to cool down the sample, which allows particles to form, which we can then collect and weigh with our filter setup. There are mixing baffles that ensure the flow rates and again, the sample itself is adequately mixed within the tunnel. The main component of the LEMS is the sensor box itself, or one of the main components. The dilution tunnel collects the stove emissions and supports the sample probes, which can be seen on the top right is a view inside of the duct, showing the sample collection probes as well as the flow grid, which is a pitot tube velocity measuring sensor. Inside the sensor box itself, there are sensors that measure the CO concentration, the CO2 concentration. We measure the particulate matter concentration, the flow rate inside of the duct, and the temperature inside the duct, as well as the temperature of water in the pot. During a test, that sensor box is connected to a computer, and the computer is running a data logging program. The example shown here is a custom application called Musa Plotter, which has been designed in conjunction with the LEMS. Other programs like LiveGraph, some of you with older LEMS systems may be more familiar with, but any of the data logging programs are used to read the data from the computer as it is being written by the sensor box. The data on the screen can be scaled and changed without actually affecting the data that's being written. So again, in real time, you're able to adjust the view. You can change which parameters you're looking at. This example here is from a sensor box that has a few more extra thermocouples, so we can check at least another 8 temperatures and a few other things on this box. But again, the view itself can be scaled depending on the stove that you're testing and depending on your preference there. So the gravimetric system of the LEMS is broken down in the small diagram on the top right here, mainly consisting of a pair of particle separators or cyclones, which will take any particles greater than 2.5 microns. So the 2.5 in PM 2.5 refers to the micron size of those particles. So the cyclone will remove any larger particles so that only particles less than 2.5 microns will be collected by our filters. The gray cylinder in line with the cyclone is our filter cassette holder, which holds a 47 millimeter glass fiber filter which is inside of a cassette with a small metal screen. You can see a used filter on the bottom right. The sample size gets doubled for stoves with less than about 5, because this is 5 micrograms per minute. When the 10 microgram resolution balance is used, or only one can use a 1 microgram resolution balance. So for very, very clean stoves, 2 filters will be ran in tandem to collect an extra, or collect enough particulate to measure. A vacuum pump is used to draw the sample onto these filters and ensure that a sufficient flow rate is maintained. Not pictured here is a critical orifice, a small device, again, that ensures that the flow rate through the gravimetric system is always maintained at a specified rate. This flow rate is also controlled, again, by the critical orifice and monitored by the rotometer. And the rotometer is also not accurate if the sample air is wet, which can happen during a water boiling test. We'll have some high humidity sample air coming through. So a small desiccator, which is the blue cylinder to the left of the rotometer in the image, is used to dry out the sample. Weighing the filters to measure that particulate matter sample, we use a 10 microgram balance for tier 4 stoves, but a 1 microgram balance for tier 5 is necessary. We condition the filters in a desiccator for 24 hours to control moisture on the filter. Again, the water boiling test results in a moist sample and often a moist filter as well. So we place that in our desiccating chamber, the black box here, for about 24 hours to dry that down to a level we can get an accurate measurement. We record these environmental conditions during the weighing session, so we know the temperature and the humidity of the lab. We use a certified calibration weight to ensure accuracy and precision of the scale before any weighing session. Each filter gets weighed 5 times, and an average is calculated. We then weigh the filter another 5 times after conditioning for at least another 6 hours to ensure that the weights agree. A desiccator with a lower humidity dries the filters faster. Ours in the lab is set around 25%. So once we have all of our measurements, we need to ensure that the data that we've gathered is accurate and is of high enough quality to be used for an ISO certification test. So quality control activities are needed for each measurement that we take. One of the main and one of the easiest and, I would say, oft overlooked quality control checks is just a simple leak check. So in this image, we are doing a leak check of the gravimetric system, of the cyclone and the filter holder. To do a leak check, you need to put the system under pressure and measure if there is any pressure drop. So you can see we are monitoring the vacuum gauge over the course of 1 minute after drawing a vacuum through the system and closing it down. And leak checks of, leaks of anything greater than just 0.1% of the sample flow rate would result in a failure of the test. So even a small leak can drastically affect the data gathered. So if we do find any leaks in the system, it's important to do this before performing a test so we can address the leaks and ensure quality data. Throughout the test, we are monitoring the gravimetric flow rate, which again needs to be maintained at a certain rate throughout the entire test. There's a small cutaway of the critical orifice that I mentioned earlier, which again is a small metal, essentially a pipe fitting with a precision hole drilled through it that allows for a very specific flow rate to be maintained. In the case of ISO 19867, it's specified that the gravimetric flow rate must be within 3% of nominal throughout the entire test. So we are monitoring with the rotometer throughout, and if we notice that it drops, then the test phase will need to be thrown out, and the system needs to be addressed. We calibrate the flow through the dilution tunnel using our a velocity traverse, which is a lab procedure involving a pitot static flow grid. You can see clamped to the outside of the ducting in the left picture, and a image of the pitot itself in the center. As long as the flow grid is clean and not deformed and free of leaks, the calibration will hold. The horizontal and vertical velocity traverse, which again is done over 12 points in total, uses the standard pitot-static probe and measures the volumetric flow rate at a given dilution setting. And we monitor this with a inclined manometer, which is a very sensitive pressure gauge. You can see with the red dye in the image on the right side of the slide. I mentioned earlier that the gas sensors inside of the sensor box get calibrated and checked with a set of known calibration gases. And before and after an ISO test, bias checks and drift checks are also performed. So the bias check is comparing the sensor's reading against that known concentration gas to measure how far off the readings are. Hopefully not far. The standard says that bias needs to be plus or minus 5% of the scale, and drift within 3%. So we check zero as well as span, which is a higher concentration gas, using known gas cylinders, again, before and after any period of stove testing. We tend to recommend large gas tanks just to ensure a multi-year supply. This is one of the more difficult to acquire items in the LEMS equipment set. And both bias and drift checks require two different reference points again. So a zero gas is used as well as a higher concentration gas. To weigh the filters, the standard says that a certified calibration weight shall be weighed at the beginning of the weighing session and at least every 10th filter to check the accuracy and the precision of the balance. So again, a small, in this case, 500 milligram calibration weight is used. We keep detailed records of every session that we perform using our balance in the lab. Once our data has been gathered and validated, a computer gets used to generate all of the final metrics and results. So all of our measurements, again, the temperatures, the masses, the concentrations of pollutants, the air velocity, all get put through our data processing software, and the end result is a easy to read and easy to compare performance metrics table. An example of this is on the right. The data processing also allows us to graphically view and visually compare different aspects and different parameters of the test. This is a screenshot of the newly developed data processing app. It's a Python-based application that Jaden, one of our engineers here at Aprovecho, has worked diligently on for quite some time now and produced a very easy to use, rather intuitive way to process the large amount of data that gets collected during an ISO test. It's available both on our Aprovecho Google Drive as well as our GitHub for anyone interested. Once the data gets processed at its basic level, considered level 1, which will get a table of results, we're also able to compare multiple tests. So for a full series of ISO tests, generally there would be 5 tests used to result in the average. We would open a level 2 in our data processing, select all the tests we would like to compare, and the application will roll that into a, again, very easy to read and easy to compare table that provides all the key elements. And again, that kind of brings us to the end. This was a fairly brief overview of both the test methods and the equipment that we use. Can open up to any questions at this point, but wanted to make sure that we give a thank you to the Osprey Foundation, who has made these webinars possible, and a reminder that 3 weeks coming up on July 23rd, Jaden will have another webinar going into much greater detail on how to understand and how to check your data. So we'll be talking about the calculations used, on how we convert the data into these ISO tiers, and a deeper discussion on the values that need to be checked on a regular basis, any common pitfalls and common issues that we might run into when we do process data. So again, at this point, we'd welcome any questions. Juan Carlos, good morning.
Hi, Travis. I'm Carlos. Sorry for my bad English, but I will try to explain my question.
Sure.
In the case of Mexico, in our laboratory, we have 2 hoods: a hood for the emissions from the chimney, and another hood for the emissions from the fugitive emissions. So I was thinking about if it's possible that we acquire our system lamps, but in the same system, we can put the sensors for every hood. I mean, for example, a CO2 and CO sensor for one hood, and another CO and CO2 sensor for the other hood in the same lamps. It is possible or not?
Not necessarily with the way the lens is currently set up.
Okay, maybe it's better to to have.
Are you running both hoods at the same time?
Yeah, at the same time. Yeah, and the problem is that I only have a system, but it's an old system. And for the other line of emissions, I have another equipment, not like these ones, but I have another ones.
Okay. I mean, in theory, yes, there is an ability to add additional sensors, but in that case, I don't. I would be concerned about keeping the data stream separate.
Okay.
Yeah.
Well, ma'am, okay. Thank you for your response and for your help in another question that I had in the past. Thank you.
Absolutely.
Travis,
Morning, Derek, or good evening.
good evening. How are you, Travis?
I'm excellent. Yourself?
Perfectly well. Okay. This is for clarity. You mentioned that if water doesn't boil within 30 minutes, you do an extra test to ensure that the water can boil.
Correct.
I don't know at what temperature do you assume that maybe it has not boiled. Maybe if it is at 80 degrees or 85, then you do an extra test. And if you do an extra test, for how long do you intend to conduct that run? Is it like 1 hour? And if it exceeds that period, like, do you kind of cancel the stove test? What would be your validation for that? Is the question
Yes.
clear?
Absolutely. So the standard says that the stove needs to reach within 1 degree of local boiling temperature. So if you boil it at 98.5 degrees local, the stove would need to reach 97.5 at some point. I would need to double check the actual standard to see if it mentions a 1 hour limit, but I believe that it says at any point. So if it hasn't boiled after an hour at full high power, then I think that we could generally assume that it would not boil at any point after that. But I believe the wording in the standard itself is at any point. So you could do it for 2 hours if you were really convinced that your stove is going to boil water, but at a certain point, I think you're able to just consider it a failure if it's not going to boil.
Yeah, to confirm on that, yeah, it's at any point. If your stove is not going to boil, you're going to see the temperature start to stagnate. So like you'll reach 70 degrees and then you're not really going to see progression on that temperature for a while. And that's an indicator that it's not going to boil. And the remedy for that is either to use a smaller pot or you can use less water. But usually it's too wide of a diameter of a pot for that stove at that fire pond.
Awesome. Thank you, Jen.
Thank you, Travis, for your presentation. My name is Tasfai Ordofa. What is the standard value of emission test? And how much of the test is harmful of or benefit of standards?
I'm sorry, can you repeat your question?
Yes. What is the standard value of emission test?
The standard value of the emission test. I'm sorry, I'm not quite sure I understand.
the cost of emission test is on when you customers came with our two according to standards. The emission test is on stove is when it's doing on stove or charcoal pellet you anywhere. How many standard value of emission?
How many standard value?
Emission test.
Are you asking if there's a range for the CO and PM emissions that you're wanting to, that's average?
Yes.
That's gonna vary a lot by whatever stove and stove design you have. Even like small changes within the stove design can drastically change those values. A good reference point is the Clean Cooking Catalog. The Clean Cooking Alliance has a Clean Cooking Catalog. It has all of the stoves that are on the market pretty much that have been ISO tested. So you can find any charcoal stove that's been ISO tested, it will have the test report for that stove. So if you kind of want a reference for a stove you're testing, you could try and find one that's similar. It's never going to be exact, but it can be a good double check that things aren't wildly out of what you're expecting.
Thank you.
Everton, you can go ahead.
Yeah, thank you. Thank you, Travis. My name is Everton. I work at Creek in Perry. I was just asking, or maybe it might be an inquiry, that we have been attending these trainings, and are we going to get certified that we have undertaken the trainings, or to as a clear proof that there is a training we had been attending?
Again, I'm so sorry, you were breaking up a little bit at the end there.
Okay, my question is, we are attending this training, but we are not sure of after the trainings, are we going to be satisfied by getting a certificate to show that we are attending this program?
I don't believe so. Our intention with these webinars is to simply provide information and ensure that hopefully all of our labs around the world are able to perform this test to the best of their ability. There's a lot of common questions that we end up getting and common concerns that we address. So we thought that providing them in a series like this would be just a nice, helpful bit of extra training for anyone working in these labs.
Okay, thank you.
Absolutely.
Travis, Derek here back.
Hi.
I have okay. We've had a couple of discussions regarding test phases with the Jardine, and I think for the first scenario is initially we are conducting firewood stoves with single phase because it was a bit challenging to really regulate and monitor airflow and feeding. That was for single phase, and nevertheless, of course, I explained that even some clients kind of request for single phase testing for their
Sure.
stove. And one of the things like she really highlighted was for a full ISO test, it has to really fully go through under the 3 test phases of high, medium, and low. The issue here is just actually to come really and confirm that, because if there is any difference, you see the standard you displayed. I think even you displayed the picture for the 3 phases. For a single phase, you actually didn't display it. Under what occasions would you really do that single phase on some stoves? If you look at some thermomass stove, that was really my concern. Thermomass stoves, which are really having a lot of ceramic, those ones would take a long time to really even try to boil. Within 30 minutes, the temperature is like 40 degrees of water. Like that is 30 minutes.
Right. Again, that's a scenario where it would be worth doing an extended length high
Yes.
power phase just to ensure that the water will boil.
Yes. So my question is basically that if at all, of course it will boil like after 40 or after 30, after 40 or 45 minutes. But after 30 minutes, it's 40 degrees. Then remember, you have now to reduce the number of sticks you are feeding for the middle phase, you get? And of course, the stove has not attained the thermal equilibrium. Then you go to medium and high power, medium and low. So I think we've kind of tried to really now consolidate the 3 power phases. But initially, we would think that maybe some stoves which will take a bit of longer time to attain thermal equilibrium would actually be falling under a single power phase of 60 minutes.
Yeah, I believe the only provision for a single phase may be for stoves that only have 1 power level. So, you know, if it was a charcoal stove with no door, with no air adjustment, could be a single phase, I suppose. But otherwise, no. If the stove has any means of adjustment, be that an air control, or in the case of a firewood stove, it's the amount of fuel. It is one of the requirements, and yes, I could see how a high thermal mass stove might suffer, but it's also probably more of a true reflection on the thermal efficiency of the stove. If we need to put energy into heating up the stove body, then that's energy that's not going into the water. So yes, it may be disadvantageous to a high thermal mass stove, but in terms of the comparison it provides, it is accurate.
Okay, thank you, Travis. Yeah, we confirmed that. Of course, we've shifted to that 3 power phases to confirm that. So I was just kind of inquiring and asking just for confirmation. But at least we've really kind of moved to at least 3 power levels for stoves which you can actually regulate either feeding or air intake. I think that has been the case. Then on another question is, if you look at the standard for institutional cook stove vis-a-vis the ISO 19867, we could see that institutional cook stoves, okay, stove is considered to be institutional, if I can recall, if it is 100, is it 120 liters and above? I think I have to confirm that. But stoves which are below, like those ones of 15 liters, 20 liters, 30 liters, still could really be operated under the ISO standard, this current 19867. That's what I wanted, like, kind of to confirm, like at a range of which stove models and size would this current test method be subjective to, and which are those ones which can be excluded and be transferred maybe to to another standard. But the institutional stove test standard kind of categorizes stoves to be institutional when it is like 100 liters above.
Again, I would need to go back and look through the standard myself. I don't believe there's any real reference to stove size necessarily. I think it's more, yeah, I believe it categorizes all stoves. But again, I would need to go double check and get you a real answer on that, Eric.
We have tested institutional stoves on the LEMS with that ISO standard. Again, I would have to check too if that is the required way. But your limitation for the LEMS is just that CO2 sensor maxing out if you have a very high powered stove. So you'll just want to make sure you're maxing out the dilution flow rate if you're going to test a institutional stove, but it does work to emissions test it that way. I think that would just be more of a request by the client on which test method they want.
Okay, thank you, Jaden. Finally, sorry for over asking this, but I saw you displaying the durability and safety. I think we've not really had like extensive part for the durability part. It's really been one of the key things for the aspect of durability. I don't know if Jaden, you've really conducted an extensive durability test as displayed or demonstrated in the standard for all like the 8 parameters, because it's one of the challenges we've really experienced. We only do the extended run, the quenching, and maybe visual inspection, whereas a full like test for ISO we consider it like to have like the emissions, the fuel use, the safety and durability. I don't know if we could really have another, I don't know if we have had it or we could have another session for durability part in that regard.
Yeah, if a durability and safety seminar or webinar would be helpful for people, I can probably add that to the list. It kind of brings up a point. If anyone else has topics that they think would be useful to review or learn, please contact us and let us know. We've already now decided to extend this webinar series because we thought of other topics that might be helpful. But it's great to hear from the people actually attending if there is any topics that we missed that we can help out with.
I think Jaden, no question.
Okay, well, if there's no other questions, again, I'd like to say thank everyone for attending today. Hope you're able to gain a little bit of information about it. Again, as Jaden mentioned, please send emails with any further questions, any suggestions for webinar topics. We would love to hear them. And again, thank you and enjoy the rest of your days. Hopefully we'll see you in 3 weeks.